All right, we're going to look at techniques to solve inequalities. That ranges from linear inequalities to quotients and other forms of inequalities. But before we start, you actually need to know the few basic things about inequalities that you've done probably at a much lower level. One of them is if you multiply both sides of an inequality by a negative number, you must reverse the direction of the inequality sign. So we are saying, let's say if I have minus x is greater than 2, if I want to make x the subject of the formula here by removing this negative, it means I'm multiplying with x both sides, or I'm dividing with x both sides. So negative times negative gives you positive x, negative times that 2 gives you minus 2. We are supposed to do this. That's one of the rules. Basically, this emanates from the idea that what we are doing here is if x is greater than minus x is greater than 2. If we don't want a negative sign here, which means we just have to swap this. If we take this side, we know it becomes positive x. And if we take this side here, it becomes negative x. So it's now minus 2. It now reads minus 2 is greater than x, which in simple terms is simply written like this. So it's just a matter of rearranging the values, the values of x and the numbers so that x is positive. This is what you've been doing for a very long time. So in simple terms, we just say if you multiply, it becomes we change the sign. You need to be more careful if you multiply and divide both sides of an inequality by a variable or an expression. So if the variable expression could take either a positive or negative value, then you don't know which direction is correct for the inequality. You can overcome this by multiplying by a squared expression. Again, that's a very important point here. One of the points that we are saying is if I say I have x squared, let's say x squared is greater than x. So the temptation, I mean, you can take it from this side, take it from the equation point. If x squared is equal to x, so the temptation of solving an equation here is you can say, let me divide the variable x, because we're trying to solve for x, isn't it? So you can say, let me divide for x. If I divide both sides by x, I get x is equal to 1. Is this true? Yes, x is equal to 1. That's true. But that's not the only variable number that gives you these two. X squared is equal to x, because we can also check when x is 0. If I put 0 squared, it's still 0. 0 is still 0 there. So there's another number that is short. And why is that it is short? Another answer. It is because we divided by a variable. So whenever we're trying to solve for unknown variables, we don't divide them out. We can only divide numbers that are common. That's all. That's one part. So important. This is very important to always note. So the easiest thing to avoid that is to arrange everything to one side, and you're not going to have x and x minus 1 is greater than 0. So you do this, you know that you've got two situations here. Either x is 0 or x is minus 1 is equal to 1 as part of the answers. Now, to know which direction, because the temptation is to say the answer is x is greater than 0 or x is greater than 1, which is actually not true in this case. The temptation to avoid this is either to use graphs, or you actually reduce this. That's when you read this part which says if the variable or expression could take either a positive or a negative value, then you don't know which direction is correct for the inequality sign. You can overcome this by multiplying by an expression squared. This is now applicable when you're dealing with quotients, inequalities that are quotients in nature. Like 1 over x is greater than x. To check this, you also need to do this. So this example I just gave here, it is much easier to see that x squared minus x greater than 0. First of all, this is a quadratic that just looks like this. So if x is 0 and x is 1, the part that this is greater than 0 is this part and that part, and hence x is less than 0 or x is greater than 1. Basically, that's the introduction to inequalities. Another important part, yes, I think this sums it all. You can try to imagine you are trying to solve an inequality involving two functions. One is this part here, which we call a rectangular hyperbola, 1 over x. This is 1 over x. And another is this part here, which we call x. That's just a straight line. Y is equal to x. That's just a straight line. So to be able to interpret the part at which 1 over x is greater than x, we look at the points of intersection, which are what we call our critical values. That's the correct term, our critical values. So from this point of intersection, you can see that the red graph, which is the straight line, lies this whole part here above the rectangular graph. Again, from this part here, which is this critical value of -1, you can see again that the black graph lies above the red graph. So we want a part which says 1 over x, the red graph, is greater than x. So it is this part here, which is -1. X is less than -1 from this point. And again, we can see that this is also existing. At which other part do we see the black graph above? So this part here, you can see the red graph is above, but from this point to this point, it is clear, check this part here, this whole part here, it is also clear that the black graph is above. So we can say from 0 less than x less than 1 by graphical means. This tells us what we have here. However, the same equation, 1 over x is greater than x, can be changed to 1 is greater than x squared. What we basically did here, we just multiplied. This is the quotient I'm talking about. We just multiplied, we removed the quotient 1 over x by multiplying by the LCM, which is x. So we get this, which is 1 is greater than x squared. And if we interpret this, this is the graph x squared, and this is the line y is equal to 1. So the critical points are between -1 and 1. And the part at which 1 is greater than x squared is this one. And that's our answer, which is from -1 less than x less than 1. Now, is this the correct answer comparing to this part? Is it the correct answer from -1 less than x less than 1? The answer is no. Why? Because we just multiplied by x here, and hence we end up getting a wrong impression of the actual solution to this graph. So if we don't have this information, or if it's difficult to solve it this way, you cannot reduce an inequality by multiplying with x, or rather with its lowest common multiple. You can only reduce an inequality by multiplying with the square of its lowest common multiple to avoid cancelling out the correct critical values. So if you multiply 1 over x greater than x, instead of multiplying with the LCM, you multiply with the square of the LCM, both sides, you are actually going to get x is greater than x cubed. And if you look at this, is our graph x cubed. And the line y is equal to x is that one. Our critical points will be this point, and this point, and this point. And we are interested in interpreting the part at which x is greater than x cubed. So in other words, we are interested in interpreting the part at which the red graph is towering above the black graph, which is this part here, and this part here. And if you see that, this corresponds to what we have on the first graph. From 0 is less than 1, from 0 to 1, and as well from x is less than x is less than -1. So you to navigate around the missing other variables, you actually multiply by the square of the LCM. That is one way of getting of answering those questions. There is another graph method which I'll show you on the last example. So here are the steps summarized. So if you want to solve an inequality involving algebraic fractions, one thing that you need to do is to multiply by an expression squared to remove fractions, not just the LCM, but the square of the LCM. And then you rearrange the inequality to get a 0 in one side, and then you find the critical values by factorization, and then you use a sketch to identify the correct intervals. So there is various techniques you can use to solve inequalities. Let us look at the first example given in this question, in this course. So we are having x squared over x minus 2 is less than x plus 1, and x must never be equal to 2. It makes sense. Why? Because if you put a 2 here, we create a 0 on the denominator. We can't divide by 0 technically. All right? So that you must always keep in mind, that your inequality is not defined if x is equal to 2. In case 2 becomes one of the critical values here, you should always remember that there is a condition that satisfies the existence of this inequality. So we are going to multiply by the square of the LCM, which is x minus 2 squared. So x minus 2 squared, to remove the fraction, is less than x plus 1. So that gives us x squared, x minus 2 is less than x plus 1, x minus 2 squared. So we continue. We now have to set this equal to 0. Oh, this was done somewhere here. Just need to remove it so that I can re-explain it. So what we're going to get here is x squared, then x minus 2 minus x plus 1, x minus 2 squared is less than 0. I don't really need to expand, because like I said, I always say it in many of my lectures, mathematicians should be lazy people. So right now what is easier to do is to find the common factors, which is x minus 2 in both the two. We are left with x squared minus x plus 1, x minus 2 is less than 0. Now we are going to have x minus 2 here, we're going to have x squared here, we are going to have minus x squared. Obviously that's x squared, then we've got minus 2, and minus 2 plus 1, that's just minus x. With this negative, it turns out to be x. And then with minus 2, then that's this, that becomes plus 2 is less than 0. That's what we have. So we are going to have x minus 2, and then x plus 2 is less than 0. Our critical values are x is equal to 2 and x is equal to minus 2. And what type of a function is this? This is just quadratic minimum graph where the roots is minus 2 and 2. So because of that, we are going to say, just remove this. Because of that, we're going to say the part that is less than 0 to satisfy this part is this part here. So our answer, therefore, our answer should be given in notes, which is x is such that minus 2 is less than x and is less than 2, where x is an element of the real numbers. And x can never be equal to 2, so you can't put an equal sign here, because x can be equal to 2. So this is your answer. Let us look at another example. Let me see if this question was done before. No. So now let us find, I'm going to do two methods here to solve this type of an equation. The first one is we are going to multiply by the LCM. So the LCM of this function, of this fraction, algebraic fraction, is x plus 1, x plus 3. But we realize that the problem of multiplying with the LCM results in us eliminating other critical values or not knowing the direction in which the inequality will go as well. So we should use the squared parts. So to remove this, we are going to say x plus 1 squared, x plus 3 squared in brackets, x over x plus 1 is less than or equal to 2 x plus 1. Again, this is very important because you can see x cannot be minus 1 because this becomes 0, and x cannot be minus 3 because this is also becomes 0, then it's undefined. But if we distribute this, we are going to have x, then x plus 1, x plus 3 squared is less than or equal to 2 x plus 3, then x plus 1 squared. We put everything to one side. Now it's going to be less than or equal to 0. That's the whole purpose. We want it to be less than or equal to 0. Now, again, we don't need to expand here. I see already common factors. X plus 1 is quite common, both sides. I also see x plus 3 is quite common, both sides. So in here we are left with x and x plus 3. Here we are left with minus 2 and x plus 1. Just have a look at my factorization. I took out x plus 1 and x plus 3, then we have x and x plus 3 minus 2. We took out x plus 3, that's gone, and that's it. That's correct. So this is quite easy to deal with because this is x plus 1 is part of the critical values, x plus 3, and in here we are going to have x squared plus 3x minus 2x minus 2 is less than or equal to 0. You could see straight away this is x squared plus x minus 2, which is just x plus 2 and x minus 1. Factorization. So what we have here is x plus 1, x plus 3, x plus 2, x minus 1 is less than or equal to 0. If I'm to the critical values, let me just write them, it's important. So critical values, normally you don't write this in the exam, you just say CV. Critical values, x is equal to minus 1, you just put comma, x is equal to minus 3, x is equal to minus 2, and x is equal to 1. Those are the critical values. What type of a function is this? That's a quadratic function, because we see that we've got 1, 2, 3, 4. The highest power is 4, so I can just draw it here. How is it moving, this quadratic function? X to the power of 4 is positive, so for the negative values the graph is is positive, so it will look like this. Okay, it will look like this. What's happening here? 1, 2, 3, 4, where this part is equal to minus 3 and this part is equal to minus 2 in that order, and this part is equal to minus 1 and this part is equal to 1. Remember, this is your y is equal to 0 and this is just f, a graph representing y is equal to f of x, that quadratic function. So we are looking to interpret this part, it is less than 0, and the part that is less than 0 is easy to identify right now. It is this part here as the part that is less than 0, and this part here as another part that's less than 0. And we are going to say x is such that, in set notation, minus 3 is less than x is less than 2. Okay? Union minus 1 is less than x less than 1, where x is the element of real numbers. However, that's not enough. I'm going to have to check again in the example above. If you check, you will see that the inequality is equal to. However, the only time when it's not going to work is when x is minus 1 and x is minus 3. So I'm going to have to be mindful of those conditions. So x is minus 1 and x is minus 3 are the only time this doesn't work. So I'm going to say at minus 3 it remains that x has to be strictly greater than that, but it can be equal to greater than or equal to 2. At minus 1 again it has to be the same, but at 1 it perfectly extends. This is the final answer. Alright.